So in this video lesson, we are going to talk about acceleration. So acceleration is how rapidly we are changing velocity or speed over time. So acceleration is symbolized with the letter A with an arrow over top, which means acceleration is a vector quantity. So it has direction. So acceleration can be talking about speeding up or slowing down. When we talk about slowing down, we often think of the word deceleration, like when you're slowing down or decelerating your car. But the word in physics is actually acceleration, no matter whether you are speeding up or slowing down. So even if you are speeding up or slowing down, we use the term acceleration with the symbol A and the vector arrow over top. So to calculate acceleration, there's a formula, and the formula says we take our final velocity and we subtract our initial velocity and we divide by time. So in this formula, A is representing acceleration, VF is representing final velocity, VI is representing initial velocity, and then T is representing time. So we are going to have to subtract our initial velocity from our final velocity and then divide by time to get our acceleration. So final velocity units are meters per second. So is initial velocity units. And then time is measured in seconds. So the units for acceleration are actually meters over seconds squared. So the units for acceleration are meters per second. That's what the m over s squared means. So we're changing our velocity by so many meters per second every second. And that's how we measure acceleration. So if we do a little practice question here, so we're going to start out, we have this car, and my car is originally going 73 kilometers an hour, and then I let it go for 1 hour, and the car is accelerating at a rate of 5 kilometers per hour squared. So that rate of acceleration means 5 kilometers per hour. So if we let the car drive for 1 hour at that rate of acceleration, after the 1 hour, our car should be going 78 kilometers per hour. So it's been 1 hour. The speed or velocity of our car will have gone up by 5 kilometers per hour. If we then were to wait, say, another 2 hours for our car, then our car would be going 88 kilometers per hour because now it has been 2 hours. So over the time period of 2 hours, our car would have increased its speed by 5 kilometers per hour over the first hour, and then by another 5 kilometers per hour over the second hour, bringing us up to a now velocity of 88 kilometers per hour. So when we're dealing with velocity or speed, we talk about something called uniform motion. And we've talked about this before, about what uniform motion means. So uniform motion means we're going the same speed in the same direction. So a great example of uniform motion is like driving on a straight highway on cruise control. So not changing our speed and continuing to go the same direction. With acceleration, we have something called uniform acceleration. And with uniform acceleration, that means we're going the same acceleration, also in the same direction. Because if we change direction, then our acceleration is also different. Okay, so we're going to do another example. It's going to be another car. Aren't my cars beautiful? So this car is originally going 75 kilometers per hour. And after 20 minutes, the car is then going 87 kilometers per hour. And then after another 45 minutes, our car is then going 114 kilometers per hour. And the car is traveling west the whole time. Okay, so one of the first things that I'm going to do is, since my velocities are in kilometers per hour, but my time is in minutes, I'm going to change my times to hours. So 20 minutes is 0.333 hours, and 45 minutes is 0.75 hours. Okay, so in this question, I want to know if this car is representing uniform motion. So does this car have uniform motion? So remember, uniform motion means that we have to be going the same speed in the same direction. So we are traveling in the same direction the whole time, but our speed is changing. So this is not uniform motion because we have a changing speed. Okay, now I want us to calculate our acceleration over that 20-minute time span. And then we're going to do the same thing. We're going to calculate the acceleration for the 45-minute time span as well. So the acceleration for the 20-minute time span, we have to do final velocity minus initial velocity over our time. So our final velocity in that 20-minute section is 87 kilometers an hour, and we're traveling to the west. And then our initial velocity is 75 kilometers per hour, also traveling to the west. And our time is our 0.33 hours. So that's getting us an acceleration of 36 kilometers per hour squared. Okay, when we do the 45-minute time section, we're using the same formula. Final velocity minus initial velocity over time. So our final velocity is 114. Our initial velocity for that time section is 87. And then our time period is 0.75. So that's going to give us an acceleration, also 36 kilometers per hour squared. Okay, so does this motion represent uniform acceleration? So remember, uniform acceleration means that we're going the same acceleration in the same direction. So that's a definite yes. We are not changing our acceleration, and we're still accelerating in the same direction. Okay, so assuming the car still accelerates at the same rate, what's its speed 30 minutes after the 114 kilometer per hour speed? Okay, so that means we have our car and it's going the 114 kilometers per hour, but we're gonna let it go for another 30 minutes, which I know is 0.5 hours, and it's going to accelerate at 36 kilometers per hour squared. And I want to know how fast it's going over here. So we're going to use our formula for acceleration. It's VF minus VI over delta T. Only in this formula, we're going to be looking for VF because we know our acceleration. So our acceleration is 36 kilometers per hour squared. VF we don't know, but VI is 114, and our time is 0.50 hours. Okay, so in order to put everything on one line, we're doing cross multiplication. So to get the 0.5 up at the top, we're going to multiply it by 36. So that's going to give us 18 is equal to VF minus 114. So then 18 plus 114 will equal our VF. So that means our final speed is 132 kilometers per hour. And we are still traveling to the west. So we're still having a westerly direction there because the car has been traveling to the west the entire time. All right. Let's do another practice question. So a squash ball with an initial velocity of 25 meters per second west is hit by a racket changing its velocity to 29 meters per second to the east in 0.25 seconds. Find the acceleration. Okay, so with this question, we have an initial velocity here. So this is our VI. And we know its final velocity, that's our VF. But I want you to pay close attention to the fact that those velocities are not in the same direction. So they are in opposite directions right now. And then we know our time, so we have our delta t. So we're using our formula for acceleration. It's VF minus VI over delta t. So to calculate our acceleration, we're going to use our VF, which is 29 meters per second to the east. And then we're going to have to subtract our VI, which is 25 meters per second to the west. And we're, of course, going to divide by our time of 0.25 seconds. Now, we know that we cannot add or subtract vectors that are not in the same direction. So we want to turn our westerly direction into an easterly direction so that we can add the two together. So to make this east, I have to make it positive. Okay, so remember when we change the direction, we change the sign of whatever the vector is that we're changing. So in that case, we're going to end up adding the 29 and the 25 and then divide by our 0.25 seconds. So that gives us 220 meters per second squared. And that's, of course, going to be to the east for our acceleration. Now, it was actually 216, but I rounded up to 220 so that we had two significant figures in our answer. We can't forget about significant figures. All right, so still working with acceleration, there is a special kind of acceleration called acceleration due to gravity. So acceleration due to gravity affects all objects on or near the surface of the Earth. And with acceleration due to gravity, we are going to ignore air resistance. So we're ignoring drag. So the acceleration due to gravity is positive 9.8 meters per second squared when we are falling towards the Earth. And the acceleration due to gravity is negative 9.8 meters per second squared if we are moving up away from the Earth. So the symbol for the acceleration due to gravity is actually a G. And G just represents what the acceleration due to gravity is on the Earth. Okay, so we are going to do 2 practice questions with this acceleration due to gravity. So a ball is dropped from a building and takes 2.6 seconds to reach the ground. How fast is it moving? Right before it hits the ground. All right, so the ball is being dropped from a building, which means our initial velocity is going to be 0 meters per second. It's going to take 2.6 seconds, so that's our time. We are looking for how fast it's moving right before it hits the ground, so we are trying to find VF. And since it's moving towards the Earth, that means our acceleration is positive 9.8 meters per second squared. So we're just going to use our formula for acceleration to calculate our VF. So our acceleration is positive 9.8, and VF we don't know, but VI is 0, and our time is 2.6 seconds. So we're going to multiply our 9.8 times 2.6, so that gets us 25 meters per second. So that's going to be our VF, and the direction for that is going to be down because the ball is moving down towards the Earth. Okay. So let's try one more practice question with acceleration due to gravity. So a coin is thrown up in the air at 12 meters per second up. How long is it in the air? So I'm going to draw a little picture here. So we have our coin resting on the ground and it's getting thrown up, but then the coin is going to have to fall back down as well. So when the coin is thrown up, its VI is 12 meters per second. When the coin reaches the top, it's going to be going 0 meters per second because it's eventually going to stop and then it's going to fall back down. And so I don't know how long it's going to be in the air for, but I do know that its delta T for its trip up and the trip down are going to be identical to each other because the coin is going to go up for a certain amount of time and then it's going to fall back down in the same amount of time. Okay, the other thing I know is that since the coin is moving up, my acceleration is negative 9.8 meters per second squared. So we're going to use our formula for acceleration. So we are plugging in negative 9.8 for our acceleration. Our VF is 0. Our VI is 12. And then we don't know our time. So that means negative 9.8 times our time is going to be equal to negative 12. So that means our time is going to be 1.2 seconds. But remember, this is just the trip up. So we're going to multiply it by 2. And that's going to be our total time in the air. So it's going to take 1.2 seconds to go up, and it's going to take 1.2 seconds to fall back down, giving us a total air time of 2.4 seconds for our coin. All right, so that is the end of this video lesson for acceleration and acceleration due to gravity. There is some practice posted for you, so you have some practice to do with acceleration and acceleration due to gravity.